How robots are learning to grip fragile objects like humans. Robots master the art of handling delicate and slippery objects with predictive control technology. Imagine a world where robots can expertly manage fragile and slippery items, revolutionizing fields like teleoperated surgery and potentially leading to fully automated surgical procedures. This vision is becoming a reality, thanks to a groundbreaking robotic control system that predicts when an object is at risk of slipping. Developed by a dedicated team of researchers at the University of Surrey, this innovative system aims to enhance the grip and manipulation of delicate, slippery, or unevenly shaped objects, paving the way for safer and more dependable automation across various sectors, including manufacturing and healthcare. Traditional robots typically rely on grip force alone to hold objects, a method that can often be ineffective or even harmful to sensitive items. In contrast, humans possess a remarkable ability to predict the movement of objects, allowing for more dexterous control. Dr. Amir Ghulamzan, an associate professor in robotics and the lead author of the study, explains, when carrying a plate that begins to slip, most people don't just squeeze harder. They instinctively adjust their hands' motion by slowing down, tilting, or repositioning to prevent it from falling. The researchers have trained robots to adopt a more human-like strategy, enabling them to sense when an object is about to slip and automatically modify their movements to maintain a secure grip. This advancement could significantly impact future automation, from managing surgical instruments in healthcare to assembling delicate components in manufacturing, sorting awkward packages in logistics, or even assisting individuals in their homes. The team evaluated the effectiveness of a technique known as trajectory modulation for preventing slips in both humans and robots. Their findings revealed that a predictive control system, utilizing a learned tactile forward model, enables robots to foresee potential slips by continuously analyzing their intended movements. Professor Venki Dubey from Bournemouth University, who was not involved in this research, noted that robots are generally trained to apply the least amount of force necessary to avoid damaging objects. He emphasized the importance of slip sensation, stating, "In many cases, we need to perform delicate manipulations, whether the object is stationary or in motion. Therefore, the sensation of slipping plays a crucial role." This capability is particularly beneficial for teleoperated robotic systems in surgical settings, where operators are not physically close to the object. If we can detect when an object is slipping, we can adjust our manipulations accordingly, he added. Integrating slip sensing with normal force sensing could significantly enhance teleoperated manipulation, especially in sensitive situations like dealing with arteries or other internal masses in the human body. This integration would provide a more realistic sensation of the tasks being performed. Furthermore, predictive control systems could be adapted for fully robotic surgical operations in the future by incorporating force sensing. The researchers at Surrey also demonstrated that their system is effective on objects and movement paths it was not specifically trained on, showcasing its potential for generalization in real-world applications. Dr. Ghulamzan expressed optimism about the future, stating, "We believe our approach holds significant promise for a wide range of industrial and service robotic applications, opening new avenues for integrating robots into everyday life. We hope our findings will inspire further research in this field and advance robotics as a whole." This research was conducted in collaboration with the University of Lincoln, Toshiba Europe's Cambridge Research Laboratory, Arizona State University, and the Korea Advanced Institute of Science and Technology. The study has been published in Nature Machine Intelligence. Are you interested in staying updated on the latest engineering innovations? Subscribe to the Professional Engineering Newsletter for essential updates on cutting-edge engineering developments and exciting job opportunities. Content published by professional engineering does not necessarily reflect the views of the Institution of Mechanical Engineers. What do you think about the potential of robots in delicate tasks? Could this technology change the way we approach automation in sensitive environments? Share your thoughts in the comments below. Share published on previous content of this nature. Breakthrough robot skin with human-like touch, faster reflexes. Future tech revealed. Imagine a kind of robot skin that can sense touch and respond faster than any human reflex. A game changer that could revolutionize how machines handle delicate tasks. This breakthrough isn't just sci-fi. It's happening now with a new fabric-based sensor developed by researchers at the University at Buffalo. But here's where it gets controversial. Could robots with such advanced tactile abilities eventually surpass humans in tasks requiring fine motor skills, raising ethical questions about our reliance on robots in surgery, manufacturing, and even prosthetics? Robots today excel in many areas, from performing complex calculations to assembling products quickly and with high precision. However, one major challenge has persisted: their ability to detect and respond to nuanced touch and subtle movements, something our human skin and nervous system handle effortlessly. This limitation restricts robots' effectiveness in situations demanding gentle and adaptive gripping, like handling fragile objects or collaborating closely with humans. Now, this challenge is being addressed through an innovative electronic textile, or e-textile, designed to simulate the way human skin senses pressure, movement, and slippage. By integrating this sensor into robotic fingers, the team at UB has created a system that can adjust its grip strength instantly, tightening when an object starts to slip and loosening just enough to avoid damage. This leap in responsiveness brings robotic dexterity into a new realm, with exciting implications for fields ranging from manufacturing lines to the operating room. Jun Liu, the assistant professor leading this research, highlights the far-reaching potential of this technology. He envisions robots that not only perform assembly and packaging tasks alongside humans more safely and effectively, but also surgical tools that can sense subtle touch feedback and prosthetic limbs with lifelike sensitivity. This isn't just about adding a fancy sensor. It's about redefining how machines and humans interact tactilely. What makes this sensor particularly remarkable is its speed. It operates on the tribovoltaic effect, a phenomenon where friction between certain materials generates a direct electric signal instantly. When mounted on 3D printed robotic fingers connected to a compliant gripper, the sensor responded to touch events in as little as 0.76 milliseconds, and never slower than 38 milliseconds. To put that in perspective, human touch receptors respond between 1 and 50 milliseconds, meaning these robotic sensors are at least as fast, if not faster, than our own nerves. Ehsan Esfahani, associate professor and co-author, notes that this responsiveness is crucial for real-time grip adjustments, a feature long missing from robotic hands. In a compelling test, the robotic gripper held a copper weight firmly. When the researchers tried to pull it away, the sensor detected the slight slip and automatically increased grip strength, just enough to prevent the object from falling, without crushing it. This kind of dynamic adjustment mimics the nuanced control of the human hand, a major milestone for robotics. PhD candidate Vashan Gautam, the study's lead author, emphasizes that their sensor not only measures pressure, but uniquely senses subtle shifts and movements of objects on the fabric surface. This flexibility and sensitivity resemble human skin's complex functionality, which is essential for fine motor skills. Looking ahead, the research team plans to enhance the technology by incorporating reinforcement learning algorithms. This approach will allow the system to continually improve its grip control through experience, adapting to different objects and tasks more efficiently. Envision prosthetic limbs that learn to hold your coffee cup just right, or surgical robots that can delicately manipulate tissues with precision beyond human capability. The team is also testing how this sensor can be adapted to various robotic platforms, expanding its applications in industries where touch sensitivity and dexterity matter most. Funded by the University at Buffalo's Center of Excellence in Materials Informatics, this study marks a significant advancement published in the prestigious journal Nature Communications. But here's the thought-provoking question. As robots gain sensory capabilities that rival or exceed human touch, how will that redefine the roles we entrust them with? Are we ready to cede even more responsibility to machines, especially in critical areas like surgery or personal care? Could this tech widen the gap between human ability and robotic precision? And what ethical dilemmas might emerge from that? We invite you to share your thoughts. Do you see this new robot skin as a breakthrough that will enhance human-robot collaboration, or as a step toward machines potentially overtaking human roles? Your perspective matters. Join the conversation and let's explore the future of touch technology together. Revolutionizing touch, Type 2 mechanoreceptors, and e-skin technology. Ever wondered what it would take to give machines a sense of touch as keen and nuanced as our own? That's exactly the puzzle a team of researchers set out to solve. Blending neuroscience with cutting-edge engineering in a way that could redefine how robots and prosthetics interact with the world. But here's where it gets controversial. Can artificial skins ever really match the sensitivity and adaptability of human touch, especially across large, real-world surfaces? Let's dive in. Imagine losing your sense of touch. Picking up an object would suddenly become a guessing game. Interacting with others would feel alien, and you'd be dangerously unaware of harmful stimuli. Touch isn't just about feeling. It's about survival, socialization, and dexterity. Our skin is swarming with specialized sensors known as mechanoreceptors, each designed to pick up on different tactile nuances. These fall into four major groups in the glabrous, hairless skin, slowly and rapidly adapting Type 1 and Type 2 receptors. Type 1 mechanoreceptors, like Merkel discs and Meissner corpuscles, are near the skin surface and provide precise, localized information. Type 2 receptors, Ruffini and Pacinian corpuscles, buried deeper in the skin, detect stretching, sustained pressure, and vibrations over wide areas. Think of them as the skin's wide-angle lens. This natural, overlapping network lets us sense the lightest brush and the heaviest grip, the faint vibration of a spider's step, or the contour of a key in the dark. Bringing this level of tactile sophistication to artificial systems could revolutionize collaborative robots and bionic limbs, making them genuinely responsive and safer for people. For example, imagine a prosthetic hand that can not only grasp objects, but interpret texture and pressure, guiding its motion with real-time sensory feedback. But implementing this is another story. Here's the twist. Most electronic skins, e-skins built today, use rigid, grid-based sensors. Great for lab tests, but often clumsy and inflexible in real worlds with complex surfaces and unpredictable movements. Even when they're designed to flex and stretch, these e-skins usually lack the nuanced processing that human mechanoreceptors bring, especially for spatially distributed and dynamic touch stimuli. Recently, though, fiber Bragg grating (FBG) sensors have emerged as game changers. These optical fibers can include multiple sensing points along their length, mimicking the distributed nature of natural mechanoreceptors. One fascinating finding? FBGs deeply embedded in soft silicone can behave remarkably like Ruffini corpuscles, a Type 2 mechanoreceptor, responding to stretch and pressure in a way that maps well onto biological function. But here's the part most people miss. Mimicking the sense of touch isn't just about laying down clever sensors. It's also about how the brain, or in this case, artificial neural networks, processes this complex web of signals. The cuneate nucleus in the brainstem acts as a critical relay, integrating and transforming touch inputs spatially and temporally before passing them up to higher processing areas. The research team took this quite literally. They built a curved, forearm-shaped e-skin packed with 21 FBG sensors, each wired to a virtual network of 126 synthetic mechanoreceptors, both SAI and FAII, mimicking their biological counterparts. These feed into a sophisticated two-layer spiking neural network, SNN, modeled after the cuneate nucleus, complete with 1,036 second-order synthetic neurons and inhibitory circuits inspired by real biological organization. Why go through so much trouble? Because real touch is incredibly dynamic. It's not just where and how hard you press, but when and how those inputs interplay. Their approach allowed them to convert nuanced temporal and spatial patterns, think differing frequencies and intensities, into meaningful touch localization, even over a large patch of artificial skin. The team didn't just claim success, they measured it. After training the network, the SNN could localize applied touches with a median error of just 14 millimeters, especially in regions with higher sensor density, a result strikingly close to the tactile acuity of the human forearm. That's not all. The system was robust even in edge cases and could distinguish two closely placed contact points, passing the two-point discrimination test with thresholds consistent with human physiology, about 42 millimeters on the artificial skin, matching the biological range. They also explored how the network could encode stimulus intensity. Stronger touches triggered more intense, widespread firing among the synthetic cuneate neurons. This matches the way real neurons respond to increasing pressure or larger contact areas, validating the model's neurophysiological plausibility. But here's where the controversy heats up. Is a neural model grounded in biological architecture actually superior to traditional engineering approaches? The researchers put this claim to the test, comparing their SNN-based localization to direct processing of FBG readouts. The neural network approach consistently outperformed the simpler method, not just in accuracy, but in the ability to generalize to new or complex stimuli. The design's flexibility opens some bold doors. For prosthetics and brain-machine interfaces, this means a future where artificial limbs can deliver natural, intuitive feedback to users, potentially via invasive neural interfaces or even non-invasive wearables. In industry and robotics, embedding such e-skins could let collaborative robots operate more safely and intuitively alongside humans, navigating chaotic environments without causing harm. Yet, hurdles remain. The bulkiness of current optoelectronic systems makes real-world integration challenging. Advancements in miniaturized photonics could tip the balance soon. On the computing side, neuromorphic hardware, chips modeled after biological brains, holds promise for running these event-driven neural models efficiently, in real time, potentially leapfrogging today's power-hungry AI accelerators. And here's a thought-provoking question. Is the cuneate nucleus, rather than the cerebral cortex, the true mastermind behind our sense of touch's spatiotemporal decoding? This model suggests it might be, challenging decades of focus on the higher brain as the primary site for spatial integration. But the jury's still out, since direct recordings from this deep brain structure are technically daunting. So what do you think? Should future robotics and prosthetics double down on biomimetic brain-inspired designs, even if they're more complex and harder to build, or are traditional engineering methods sufficient, given time and cost constraints? Could artificial e-skins someday even surpass biological skin in sensitivity and adaptability? Chime in. Where do you stand on the ongoing debate between engineered simplicity and neuro-inspired complexity?